So we're now going to look at how to handle two links to different ISPs, but with load sharing. So we'll look at a simple example first, and then follow it up with something a little bit more complex. So again, we have the AS100 connecting to the upstreams AS110 and AS120. And as before, we're going to announce the aggregate block out to both upstreams. Because our aggregate is announced, if either link should fail, we still have backup through the other operator. What we're going to do now is take the 19 and divide it into two pieces. Sound familiar? It's the same principle as we saw earlier. We're going to announce 1/20 on the link to AS110, and we're going to announce the second /20 on the link to AS120. Should either link fail, the /19 through the other link provides the backup. But what it also means is all traffic for the first /20 will come in through AS110, and all the traffic for the second /20 will come in through AS120. And yes, even traffic from AS120 going to the first half of the address space will go all the way through the internet and AS110 to reach AS100. And all traffic for the second /20 from AS110 will go all the way through the internet through AS120 to get to AS100. So that's one of the side effects of leaking sub-prefixes. They're more specific than the covering aggregate, and traffic will always follow that over the covering aggregate. Let's look at router A configuration. We're now originating the /19 aggregate and 1/20. And so the prefix list allows the aggregate and the /20 outbound. And there's another prefix list allowing just the default route in, similar to what we saw in the earlier examples. Router B, aggregate out plus the second /20, as we've seen earlier. So this is actually a very basic load sharing. It assumes equal traffic across the entire address space. And the idea here really is to show you the first steps in designing a load sharing solution. We start with a simple concept and build on it. So now we're going to look at more controlled load sharing. The previous one, we simply took the 19 and divided it into two pieces. It doesn't really give you much control. So what we're going to do now is combine the previous two techniques that we learned, subdividing address space and doing AS path prepends, to give us a little bit more control for our load balancing. If you look at the diagram, AS100 connects to 110 and 120 as before. We're going to announce our /19 aggregate out each link as before. What we're going to do now is apply some traffic engineering to the link between AS100 and AS120. And what we're going to do is take the 19 and pull out 1/20 sub-prefix and announce that /20 on the link towards AS120. Again, it means all traffic for that sub-prefix will come in through AS120. We're also going to announce the /19 aggregate towards AS120 with a longer AS path. So if you think about it, we now have two things we can adjust. We can adjust the size of the sub-prefix we're announcing to AS120. We can start with /20 and see what we need to do. And we can change the length of the AS path of the /19 aggregate towards AS120, again, to suit the level of traffic. If we have a lot of traffic for the first half of the address space and not very much for the second, we can modify the length of the AS path prepend to push more traffic towards the AS110 link, or push more traffic towards the AS120 link. So we have now two ways of tuning the load balancing in this example. We still need redundancy, of course, and that's what our aggregates do. And of course, our upstream providers still announce the default route. If we look at router A, it's a simple configuration. The default is allowed in, the aggregate is allowed out. Router B is where the traffic engineering happens. We let the default in, But outbound, not only do we allow our aggregate out, we also let one subnet of the aggregate, in this case the /20. And we have the route map ag prepend, which looks for the aggregate and does the prepend. So let's look at the prefix lists and the route map. First off, the prefix list AS120 out allows the /19 aggregate out, as well as one of the /20s. So all traffic for that /20 will come in through AS120. The traffic for the other /20, so the other half of the entire aggregate, will be balanced between AS110 and AS120. And we can change this balance by using the ag prepend route map. So if we look at that, it's looking for the prefix list aggregate on the outbound announcing, and if it finds it, it's doing a double prepend. So AS120 will see the aggregate coming to it with 3 of AS100 in the path. And you can change this. You can make it a single prepend if you're not getting enough traffic, or if there's too much traffic, you can make it 3 times prepend, or 4 times. You shouldn't need to make more than 3 or 4 prepends. More than that, there's something else wrong with the interconnectivity further out in the internet, which an ASPath prepend is simply not going to resolve. So this example is much more commonplace, and it shows how network operators and end sites will subdivide address space frugally, as well as using the ASPath prepend concept to optimize the load sharing between different ISPs. And notice we're always announcing our aggregate. As we covered earlier, it's vitally important to ensure that the aggregate is always announced on all external links. So the previous examples dealt with a simple case. We're load balancing inbound traffic flow, and we achieve this by modifying outbound routing announcements. The aggregate is always announced. We've not looked at outbound traffic flow. For now, we're leaving this as nearest exit, which is sufficient for most end sites connecting to either the same upstream provider or to different upstream providers. The next part of this series will look at how we balance outbound traffic flow, as that is a little bit more work and a little bit more challenging for network operators to achieve to their satisfaction.